variables, you can calculate the fourth. Okay, so let's do an example of one of these. Let's say we've got a container of methane that's 1 liter in volume at room temperature and has a pressure of 1,000 psi's. Okay, so let's say pressure or room temperature, depending on who you ask, room temperature is around 20 or 25 degrees Celsius. Let's say it's 25 degrees Celsius for our sakes. Okay, we are going to use our new ideal gas law equation, PV equals nRT. Okay, so R will dictate what units we need to use. And of course, we are going to use 0.08206, as we just said. So we're going to need our volume in liters, our pressure in atmospheres, number of moles in, not surprisingly, number of moles, and of course, temperature in Kelvin. Okay, so the temperature in Kelvin is 25 degrees Celsius plus 273 to give us a temperature of 298 Kelvin. Okay, 1,000 psi's. If we look back at the equivalency from the first table we showed, we remember that in 1 atmosphere, there's 14.7 psi, so that's what we can use for our conversion factor there. And that will give us a pressure of 68 atmospheres. Okay, so we're after moles, so we're going to solve for n equals PV over RT. And our pressure is 68 atmospheres. Our volume is 1.0 liters. Our ideal gas constant is 0.08206 liters, atmospheres per mole, Kelvin. And then our temperature is 298 Kelvin. So throw that into our calculator and we're going to get 2.8 moles of methane. Just to be sure that we got moles of methane, atmospheres cancel out, liters cancel out, of course Kelvin cancel out. So 1 over moles is moles, and so our final answer is 2.8 moles of methane. Okay, so the next law we can discuss is Dalton's law of partial pressures. Okay, and so this is a very simple, intuitive law, but it has a lot of ramifications about mixtures of gases. Okay, now the law of partial pressures, all it says is that the total pressure is the sum of the individual partial pressures, or the sum of the partial pressures of the individual components. Okay, we can mathematically show that by total pressure. P sub TOT equals the pressure of the first component plus the pressure of the second component plus the pressure of the third plus the pressure of the fourth, and so on until you get all the individual partial pressures. So if we look at the composition of air, we can see that the 4 main components that make up 99.99% of the air are nitrogen at 78%, oxygen at 21%, argon coming in third at 0.9%, and then carbon dioxide around 0.04%. Now notice this, we're leaving out water. This is composition of dry air, because the amount of water in the atmosphere can vary from region to region and day to day. But so if we wanted to calculate the pressure of air, it would just be the sum of the partial pressures, pressure of nitrogen plus the pressure of oxygen, plus the pressure of argon, plus the pressure of CO2. And again, those are the major components. There are, minute traces of various other gases, but we could calculate the total pressure of air primarily based on these 4. Okay, so one of the things that we're going to need to incorporate is a standard measure of temperature and pressure to discuss the various properties of gas. And this was really going to come out when we talk about the density of a gas, because as we said, we can add more moles of a gas to a given container. We're going to increase the mass, but the container still has the same volume. So density is going to, as we previously calculated, will change. So we're going to need to come up with a new definition for density, not a true new definition, but it's a different calculation. And that calculation will be done at STP. And this is standard temperature and pressure. And all this says is that we're going to define a few experimental conditions, specifically temperature and pressure, so that when we do experiments with gases and we discuss them or display data, we know what primarily what experimental conditions these experiments were held under. And if we're talking about standard temperature pressure, the temperature is 0 degrees Celsius or 273 Kelvin. The pressure is 1 atmosphere. Okay, so one of the first things we could talk about is the molar volume at STP. And the molar volume is, as the name implies, the volume of 1 mole of gas at STP. Okay, so we could do a calculation for that. Is the volume of 1 mole of a gas at STP. Okay, so if we wanted to find that, we could just calculate volume from PV equals nRT. Okay, since we're talking about 1 mole, so let's use 1 mole as our number of moles times our gas constant, 0.08206 liters atmospheres per mole Kelvin times 273 Kelvin, standard temperature, divided by standard pressure, which is 1 atmosphere. Okay, that gives us a volume of 22.4 liters. Now the trick question for this calculation is 22.4 liters. That's the molar volume for what gas? Is it hydrogen? Is it oxygen? Is it water vapor? Is it neon? Well, it turns out that it is the molar volume for any gas. We could incorporate any units for a gas, 1 mole of neon, 1 mole of argon, 1 mole of hydrogen. That wouldn't change our calculation. So the molar volume of any gas is 22.4 liters, and so we can utilize that for several different purposes. And the first of which would be the density of the gas. Okay, so here's how we're going to calculate densities for gases. We're going to divide the molar mass by the molar volume, and this will give us a standard density that, of course, won't change on the pressure of the gas. Okay, so let's calculate the density of helium. Okay, so this is going to be the molar mass, which if we look on the periodic table is 4.002 grams per mole, divided by the molar volume, which we just calculated was 22.4 liters, and that's volume per mole, so we can say liters per mole. So that's going to give us units of grams per liter, mass over volume, same units we always use for density. But because gases take up so much room, so much more room than solids or liquids, we use liters as our volume, or units for volume. So that calculation gives us a value of 0.178 grams per liter. Okay, if we compare that to the density of nitrogen, which is density, the molar mass of nitrogen N2 is 28.014 grams per mole. Molar volume, nitrogen, 22.4 liters per mole. Those are going to cancel. And if we throw that in our calculator, that's going to give us 1.25 grams per liter. Okay, and so you can see that because of these densities, that's why, of course, our helium balloons float in air, because air is primarily nitrogen. Helium is much less dense than nitrogen, and just like solids in a liquid, the less dense substance will float. All right, so let's do another calculation that we can use utilizing our information here. It turns out that if we know the mass of a gas at some experimental conditions, we can determine its molecular weight. And this, historically, this was the method that the initial molecular weights of many substances were determined, before mass spectrometry was around. Okay, so we know that the units of molecular weight is grams per mole. If we know the mass in grams of our substance, we can calculate the moles using our ideal gas law, PV equals nRT. Solving for n, then dividing that from the grams, we'll get the molar mass. So, we've got 886 millimeters of mercury for our pressure. Of course, we are going to have to convert that to atmospheres. Okay, and so 886 millimeters of mercury. Those are the same thing as torrs, so that in 1 atmosphere, there's 760 millimeters of mercury. That will give us an overall pressure of 1.17 atmospheres. Okay, we've got 55 degrees Celsius. We're going to have to add 273 to that, so 55 plus 273 will give us 328 Kelvin. Okay, and so now we're set to calculate the volume, and that I incorrectly solved for N. PV over RT is our calculation. Okay, so our pressure, we calculated that, was 1.17 atmospheres. Our volume was 0.225 liters, divided by our ideal gas constant, 0.08206 liters atmospheres per mole Kelvin, times temperature in Kelvin, 328. And that will give us the number of moles, which is 0.0090 moles. Okay, so if we want to figure out the molecular weight of this substance, we're just going to divide 0.311 grams divided by 0.0090 moles, and our molecular weight for this substance is 34.5 grams per mole.